Y'all, this week we are studying magnetism. There is a reason that we are studying magnetism after we studied electricity. So this week we are actually discussing magnetism and electromagnetism. So there it is again, just like an electroscope, right? There's electrons again. So you better bet you we're about to talk about electrons and what electrons are doing. Going back to our basic chemistry and what's in an atom, right? Protons, neutrons, and electrons. Protons and neutrons stay in that nucleus. Electrons are moving from atom to atom and they're spinning around that nucleus. We're going to get to the spinning today. All right, so I've got some magnets from a kit from my kids. So it may not be something you've seen before, but a little science kit picked up. And you've played with them. I'm bringing them, actually, I'm bringing them within about 2 centimeters of each other, and these guys are attracted. So this must be the North Pole and the South Pole, opposites attract, right? With these, you turn them over. And now I get within 2 centimeters and I can push this guy across the table. In fact, my table must be less than 2 centimeters thick because I can move this magnet around even having a magnet below the table. Why is that? What are you feeling when you push magnets together and they want to push away from each other? Well, it's similar to what we did with those balloons that we talked about in class. So let's look at this. I'm going to bring them really close to each other, as close as I can, just about 2 centimeters. And I'm going to bring up some iron filings. So filings, these were filed off of iron, right? You could actually take an old file and file down some maybe some old nails and get these little bits of iron. And I'm going to slowly move it down toward the magnets. You might see some stuff happening already. And look at that. I haven't really touched the paper. And you can see right down the middle, it's kind of empty. These magnets really literally out here in space don't want to have anything to do with each other. Look at these lines. You can see that those filings started lining up. These are field lines in the force field around the magnet. So these are the field lines, and they're coming down, and they're coming down, and they do not want to touch. In fact, there's this empty space in between. Up here, up here. Notice, I don't know if you can see this on the camera, there's several millimeters up, the iron filings up in space are building these little towers. And it's affecting way out here, 3 and 4 centimeters away from the magnet. It's lining up the iron filings. What about that? All right, so let's keep going. I'm going to pull the magnets away. Make them a little bit random again. This time, I want them to be attracted to each other. So I'm going to put them about 2 centimeters, not too much closer, together. And slowly go down. And you can see again those field lines, but this time there's no empty space. In fact, look out here, this curve. The field line went out and it curved and connected to this one. There's a line. You see this one right here especially. There's a line. Okay, these field lines are connecting to each other. So again, these are field lines. This is the force field, right? The force field around the magnet. There's something going on around that magnet. There's something going around this magnet to cause these iron filings without us doing anything to line up and to curve. Look at this curve here. It's going out, going, no, 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 I'm really attracted to you, right? North and south, opposites attract. Well, what is it? What is it that's going on? And that's when we get to this idea of these electrons. Again, I'd like you to take some notes as you go along. I'm not going to take too many, just in this space right here. I'm going to draw a bar magnet. It's kind of like those two guys trying to be connected to each other. And then I'm going to draw a rather large iron filing. Inside the bar magnet, And the iron filings, mostly made of iron, Fe, are little groups of atoms. And those groups of atoms have something in common. And what they have in common is that the electrons within those domains, those little groups, are all spinning in the same direction, right? The electrons are spinning around the nucleus in several different orbitals from your chemistry class, from physical science in middle school, and they're all spinning in the same direction, north to south. In fact, they're spinning and they're creating a force field. And I'm drawing some field lines. Just like with lightning poles and static electricity, you just keep drawing these lines and look at it how the domains are lining up. You can see that the poles are the strongest. This is part of the reason the poles are the strongest. Okay. So again, the domains, the electrons in these little groups are spinning in the same direction. And so we end up with a magnet. In fact, the magnets that I have here are permanent magnets. If I beat on them, I heat them up, I do some different things to them, I could actually mess up the domains and it wouldn't be a magnet anymore. But I'd have to really punish the magnet for it to become not permanent, not to remain a magnet. Right, so here's the iron filings. And what's true here in this mess is there are little domains, but the electrons are spinning in all sorts of different directions. So they're not congregating, they're not lining up, they're not affecting anything else. But when I bring a permanent magnet close to the iron filings, then out there in space, those little domains line up. And they get magnetized themselves. They become temporary magnets. Again, if I bang them, hit them, take the magnet away from them, it's not going to take long before those domains are random again. Okay? All right. So one little trick you can do, I put this paper clip on my magnet and it itself becomes magnetized, right? The domains have lined up. In fact, it can be pretty strong. I'd want to maybe play a game to see how many paper clips I could line up in a row. It sort of tells you the strength of your magnet. Let me get that on the camera. So here I've got 3. Now, as soon as they fall, get jostled, the domains become random again, and no longer are my paper clips magnetized. Now, earlier, remember in the video, one of them was a little bit of a magnet still. Some of the domains were still lined up. Well, there's a misconception about what can be magnetized. So that's the next thing we need to talk about, and I'd like to show you. Here's my handy periodic table that I keep on my desk. I'm sure all of you have one as well. The three atoms that can be magnetized, highly magnetized, the ones we talk about are iron, cobalt, and nickel. The Latin for iron is ferros, right? These are the ferromagnetic material. These are the 3 that we talk about: iron, cobalt, nickel. You'll learn this week the Earth, right, is mostly made up of iron. It has an iron core. The Earth is a huge bar magnet. And because of all that iron and how the domains are kind of lined up along there, we have this great magnetic field that protects us from some of the gamma rays and X-rays that we talked about before spring break. Iron, cobalt, nickel. Not all metals can be magnetized. Now, to some extent, all metals, those electrons are going to react, but not anything that we would actually be able to see. Okay, we'd have to measure it in some different way. So iron, cobalt, nickel, to be sure, these are called the ferrous-magnetic material. These are the ones that become magnetic. Well, some of you might be out there going, Mr. Pizzillas, I know that there are neodymium magnets and that they're very strong. I actually have some at home and I play with them, right? Number 60, neodymium. Well, here's what you need to know about neodymium. Maybe the most common neodymium magnet is made of 2 neodymium atoms, 14 iron atoms, and 1 boron atom. It's mostly iron. What makes neodymium really, really strong is its saturation of domains that are aligned and how long it keeps those domains aligned. Because of its crystalline structure, even as a metal, it has a kind of a crystalline structure. Tetrahedral is the word that's coming to mind. It's kind of the way that it's just grouped together. It keeps these domains and it keeps them very, very strongly. And it's saturated. There's not some domains that are going the wrong way. They are almost all totally pointing in the same direction. Okay, so we have these 3 ideas. One more set of notes before a little another demo. So again, all of this is about electrons. Everything that we've talked about for several weeks now. We talked about static electricity, right? Where electrons get stuck. So we rubbed a balloon on some hair, right? The hair got positively charged because the electrons moved away. Now, the gentleman with the Van de Graaff machine filled his hair with electrons and they stuck in his hair. They stayed in one place. We've talked about circuit electricity, electrons that flow in a circle. So I'm going to draw a couple cells, a battery, and a resistor, a second resistor, and a third resistor. Notice these are in series, connected by wires. And the electrons flow from the power source through the wires through the resistors. You can kind of think of that as a big current, a big flow in a circle. Well, magnets are our third way, last way that we're going to talk about electrons. In a magnet, whether it's permanent or temporary, the electrons are spinning all in the same direction. Make that magnet. All right, one more idea from our notes this week, just to show you electromagnets. What is an electromagnet? Well, it's pretty cool. As we've discussed, there's a field around all these moving electrons, actually. Okay, especially the magnets. I just showed you that. So we can actually take an iron core, some wire. We can coil that wire around the iron core, in this case a nail. It's called a solenoid, okay, that coiled wire. That just puts more wire in one place, right? If I stretch that out, it'd be very long. So I can make a greater force field around those flowing electrons that are going through the wire. And of course, I need a power source. My kids have been playing with this, so this is not as strong as I'd like it to be anymore. But right, so there we go. I've magnetized this iron core. I've lined up the domains within this iron core. Notice I want to pick up something. Maybe this is a big electromagnet. I'm picking up a car to be shredded or something along those lines. I'm just getting a doorbell to ring. Right? I can pick up great things and I can turn it on and off. Right? Great thing about electromagnets, you just turn off the electricity and you turn off the electromagnet. Well, you can see it's kind of difficult to pick these up. How could I make this a stronger electromagnet? Well, one thing I could do, I could have a lot more coils. Okay, you compare these two. That one on the right has a lot more coils. Actually, coiled it about 3 or 4 times. So I could add more coils, and that way I have a bigger field that I'm working with. So we had these caps when I was in brick and mortar that I don't have at home that I'm really missing right now, but this has been working out okay. All right, you can notice I picked those two paper clips up without any trouble at all, right? This is a much stronger magnet because of the number of coils. Well, what else could I do to make this stronger? Maybe I really want to pick up something. Like, look at that. This one's even going to pick up this ring a little bit. Well, we could add more power. This is a 9-volt battery and a 9-volt battery. All right, this worked pretty well, but I'm all thumbs. So I'm putting the positive and negative together. Let's see what I can do. I played with this and this worked out pretty well a couple times. All right, don't want to take too much time. I'm being all thumbs. I need my electric tape and more coordination or something. Well, I don't know that I'm going to be able to show you now. Can you believe me if I tell you that I picked this up earlier without any problem? The batteries have been getting hot during the day. Me and the kids playing with them. All right. I'm just being klutzy now. Oh, come on. This is the last thing I have to say. Okay. Well, thank you for hanging in with me. Um, 2 ways. Sorry, I'll play with that later. Send you a picture. 2 ways to strengthen an electromagnet is the number of coils. Can we get that off? The number of coils, of course, the number of amount of power. Really cool thing about electromagnets is just how much mass you can pick up, right? And that you can turn it on and off for any of its applications. You need 3 things. This finalizes our notes. You need an iron core. You need some wire, which you are going to coil around your nail. More coils, more power. And then you need a power source. And we just used a battery. Okay? So a power source, which you can turn on and off, wire, and coils. More coils, better electromagnet. More batteries, better electromagnet. This is your nitty-gritty, right there, notes about magnetism and electromagnetism. Hope you enjoyed it. Thank you.